As promised, here is a little more complete example. Um, so what I'm going to show you today is a graph that I've looked at in a variety of contexts. And most recently, for example, this type of graph was used to try to get some sense of when COVID-19 would make its way across the world and what type of time frame it would do that in. And so this is the global air transportation graph. I am not going to give you the entire global air transportation graph because there are a variety of issues that I'll discuss in a little while. I'm going to keep things very simple, and so we're just going to be looking at the Manitoba part of that graph. Okay. Um, it still is it's not a very large graph, you will see, but we can start to perform some interesting analysis on it and try to see how the types of measures that I've talked to you about for the last little while, how you can end up using these measures. So the first thing that I'll do is I'll be using these packages. Actually, I won't be using all of them, but I'll just put them like this. And this is, for instance, when you're giving me code, this is often a nice way to do things. You see, what I'm saying is, well, if you need to install, then maybe you set this value to true and it will install these packages, and otherwise you set it to false and it just loads them at the beginning. So deployer is a package that allows to what typically we call wrangle data, which is sort of make it look different. Reader is to read files. SQLDF, I'll come back to this later. It's to deal with data frames in another way. iGraph is iGraph. ggraph, we're actually not using here. I could probably just remove it, but I don't know, maybe I will edit a little bit of this worksheet before I give it to you. And in that case, it would become useful, so we'll see. And raster, finally, is to do mapping. Okay, so we load these packages. And what I will provide you with are two files, additionally to the Jupyter Notebook file, of course. One is going to be called airtravelmanitoba.csv, and it's going to contain a description of a network. And the other is going to be airport codes Canada, and that file contains information about essentially all airfields in Canada. That includes very tiny, minute little things. You'll be able to take a look at this. This is open data that you get online. I'll explain to begin with the type of data that you have there. So as a sort of word of warning, this data, well, it's not a word of warning, that data that you'll have there have essentially anonymized. The full data set is a massive data set. So the file that I generated, the file that I'm giving you from, contains almost 3 million lines and 19 columns. And it's actually, that file itself is a snapshot of a much larger file. And so those files, what they give us is for a given period of time, it will detail all the trips that are taken worldwide between all the airports that are in this database. And that database contains something like about 4,000 airports. And not only does it contain the origin and destination, but it also contains intermediate stops. Okay, so for instance, if I go back to where I come from in France to visit my family there, I would fly probably Winnipeg to Toronto, Toronto to, often I fly through Germany, so let's say Toronto to Munich, and then Munich to Toulouse in the southwest of France. And in my database, I will see this as one itinerary. It is going to be aggregated over some time period. And so if other people do the same trip as me in that time period under consideration, they would appear as one more trip. And so what you get is the number of trips following a particular itinerary over a time period. So what I've done from this, because this is a very expensive data set, we can use it only under very specific circumstances, and we cannot give it out. So I've taken a very small subset, and I've also, first of all, you don't know when this is happening. I'm not telling you the month or the year for which this is done. And the other part is that I've cut out this information about partial trips. What I've done is that if the trip that I was talking about before, so Winnipeg, Toronto, Toronto, Munich, Munich, Toulouse, for example, if I had five trips like this over a time period, what the data set that I am going to provide you with would show would be one trip from, well, 5 trips from Winnipeg to Toronto, 5 trips from Toronto to Munich, and 5 trips from Munich to Toulouse. So in that sense, it becomes impossible to deaggregate the information. And the reason I have to do this is that this is, as I said, data that a company charges for. So in this form that I'm giving it to you, it's impossible to tell exactly what's happening. And so in that case, it's not a problem. Okay. So this being said, so what you'll get is a list of edges, okay, or arcs actually, because it's an oriented graph. And those arcs are going to describe the number of people flying from one airport to another airport in Manitoba over a time period. Now, what I'm going to do is I'm also going to, and I'm not going to use it much, but just for completeness, I'm also considering the rest of the world, because of course Manitoba's transit network, air transit network, is not isolated from the rest of the world. And so I've introduced another vertex. So the vertices in this graph are going to be the airports. And what I've done is I've added a vertex that I've called rest of the world that represents everything that is not in Manitoba. So it's a very artificial thing. It is not realistic in the sense that all the airports in the rest of the world are distinct. But in this particular case, what we're looking at is one particular vertex that actually represents all of this rest of the world. And you'll see in a very short time what this looks like. Okay, so, and I've described this. Again, one of the advantages of Jupyter Notebook is I can mix code and text. So here I've got some text where I'm explaining the problem. Now I'm going to load this file, these two files. So Air Travel Manitoba is going to be the network itself, the graph. And airport codes is something we're going to use because what we want to do is, for example, when we're representing the graph, we want to plot the vertices where the airports actually are, okay? And so this file, which is about 400 kilobytes, contains all the airports in Canada. And so what I'm doing here is I'm using deployer. So this is a pipe, and you load the capacity to use the pipe by loading this library deployer. And what that says is the result of this function, pipe through, as in Unix pipe, so go into the next thing, and that next thing is filter. So as the name implies, it's going to filter out the data, and that filter says that ISO region, which is going to be one of the columns in this file here that we've loaded, ISO region has to be Canada slash dash Manitoba, which is an ISO code for Manitoba. Okay, so when you do that, and then you ask to see the top of the files, you get the following. So this is using read delimited, by the way, because that file is, oh, I could have used read CSV, but this is part of reader. Okay, this is part of this library here, reader. So I'm loading these two files. I'm filtering out whatever is not Manitoba in the airport codes. And so this is reader telling you what it's doing. It's found two character columns. That was origin and destination, and one numerical made of doubles column called volume, vol for volume. And for the second file, the airports, it's found a bunch. It's got 12 character columns, 4 double columns, and I'm not actually sure what this means. I'm not sure. LGL columns. Not sure about it, what that is. Okay, but anyway, so this is what this looks like. So the air travel has 108 rows, and those rows look things like this. So this is from the rest of the world, so origin and destination, to YBR. This is what's called the IATA code for the airport in Brandon. Okay, and it's telling me that over the period of time that I was considering, there were 2002 people that came in from the rest of the world and arrived in Brandon. This is the same for Thompson. YTH is Thompson. And in that same time period, there were 18 people that came from the rest of the world to Thompson. Rest of the world could be Saskatchewan, for example, or Ontario, or the US, for example, private flights or things like this. Okay, but we don't know this. Rest of the world to Winnipeg, that's where most of the traffic went. 160,000 almost passengers coming from, as I said, it could be the rest of Canada, it could be the US, it could be Mexico. We don't know. Then there are also flights from places in Manitoba to the rest of the world. I don't remember what the XLB is. Okay, we can find it in the airports here if we want. So there's 108 lines like this that are detailing these trips. And then the airport table is a table that contains the following information. It's got an identifier. It's got an ID, sorry, an identifier type. And you can see that the beginning of the table are mostly closed. They've just kept in the database because at one point they were airports. They might not be airports anymore, and in those cases they're probably not. What's important for us in this application is just those two numbers, the latitude and the longitude. Okay, we're not going to be looking at other things. Another thing that we will be using, so you see that we've selected, using the command here, we've selected only things that have CAMB here. This is nearby municipality, whether there's scheduled service. The thing that's going to be important as well is this IATA code, because in the table here, we are using IATA codes, And that's how we are going to be able to plot the vertices where we want them to be. And you see there you've even got information on the links to a Wikipedia page about this, if there is, etc. Okay, so we have this. And this is the first remark that I want to make. And so this is probably not very interesting for most people in the class that are not in computer science. For those who are in computer science, this is an alternative way of playing with the data that I'll mention just in passing. So a lot of people, when they do R, they use deployer. This, I think I've mentioned this program, well, this library before. I mean, not just here, but in the past. This has become a very, very popular way to deal with data. For me, I'm still not completely used to deployer. I find it very useful to do things like this, but I don't always, I find that it's sometimes complicated to use it in some cases, but I know how to do very well using what's called SQL. So for the non-computer science people here, SQL is a database specification language, but it's very, very powerful. It's become a little, I mean, it's still used enormously. There are more flexible ways of describing the data, but SQL remains a very, very important way of describing data. And one of the advantages I find is that it's very easy, once you've learned SQL, to come up with quite complicated ways of interrogating the data, sorting the data, and doing things with it. And this is typically what's called a query. And so what I'm doing here, this SQLDF library that I didn't load here, but that I installed, is allowing you to use SQL requests on a data frame. Okay, so here what I'm doing is I'm using SQL syntax, I'm making a query, which is to say, in my, and the data you have, you don't need to do that because I've already done this information, but this is more for the processing. This is for the information of those who would be tempted to try this. So, because remember I said I decomposed the trips by saying that, for example, someone who comes from the rest of the world into Winnipeg and then flies into Brandon is going to appear as two different instances, one rest of the world to Winnipeg and one Winnipeg to Brandon. But for instance, someone who would come from the rest of the world to Winnipeg and then move on to Churchill would also be rest of the world to Winnipeg, Winnipeg to Churchill. So that first part of the rest of the world to Winnipeg, I need to aggregate them and count how many there are. And one very, very easy way to do this is by using this SQL query, which is, let me select the origin, destination, and the sum of the volume information, but I'm just going to call volume from whatever data table I want, data frame I want to process. And then I'm going to group by origin and destination. So that means when I have two lines that are rest of the world to Winnipeg, rest of the world to Winnipeg, they will be grouped together. And the volume information in those two lines is going to be summed to give you volume. Okay, and then I simply order by origin and destination. And it is by doing this on a much bigger output that I created this file that you've downloaded here. Okay, so this is just in passing, but I think it's interesting for those of you who are in the sort of computer science more approach. And just in passing, that's interesting for everybody else. I don't know if I've done this a lot in the code so far. You don't have to make a library call like is done here at the top of the code. You can also, if you are going to use just one function from a library, you can do so like this by using the name of the library followed by 2 columns and the name of the function. Okay, so that allows you not to have to load everything, you just use that function. Okay, and so now we're ready to go. We have our description of what are going to become the arcs in our network. We also want to take this file, this data frame here, which is still big. You see this, even once we've sorted things out, we are left with almost 3,000 lines. And what we want to do is we want to keep only the airports that are actually in those arcs that we're going to use. So this is what I'm doing here. Okay, I'm getting all the codes, the IATA codes, like the airport codes, for the airports that are an origin or a destination. I'm putting all of them together. I'm sorting, but that's not important. And I'm looking at unique values. So this is going to give me the list of all the airports that are present in the connection file. And then what I want to do is I want to make a data frame that has also, for each of these airports, the longitude and the latitude, because that's what I'm going to use to plot. Okay, so I'm just creating 2 empty vectors. I'm going through those codes that are in the network description, and I'm just finding which of those lines is there. And the only thing I'll point out is if I don't find anything, I know all the airports are going to be in this database. So there is one airport that is not in this database. Remember that I've said that I was using rest of the world. And so what this is doing is it's saying, well, if I haven't found anything, it's because the airport is actually the one that I've called rest of the world. And I'm going to assign a latitude of -90, which is somewhere in the, like just east of Manitoba. And a longitude of -90 and a latitude of 49.5, so just about the same height same northerly height as Winnipeg. And otherwise, I just add the latitude and longitude. And so what I get is a list of the airports and with that longitude and latitude. Remember, longitude is left to right on the globe. Latitude is top to bottom. One easy way to remember this, sounds silly, but in France, and I think in Britain, they used to have this also. We used to have something called the Bureau des Longitudes, which was the Bureau of Longitudes, because computing the longitude is much, much harder than computing the latitude. Latitude, you can do it by observation of the sun and etc. Longitude requires much different methods. And so there was a lot of research done to try to figure out good ways of computing longitudes. So the existence of a Bureau of Longitudes reminds me that, okay, determining where you were east to west was complicated, and that's it. But that's one way to remember it. That's important later, because that's where we are going to put the vertices, which is what I'm doing here. So I'm going to use a graph from data frame. So remember this data frame here, the data frame is yes, sorry. So what I'm making the graph from, I could have done, if I had added the longitude and latitude, I would get this. The graph from data frame just takes a data frame and adds. So the one thing that is going to be added there is each arc is going to receive the property with the third, well, if you had more columns, it would have more properties. But one property it's going to receive is volume. Okay, and that's going to be important later. I'm not using it yet, but this will come in important later. So what I do here, I'm creating the graph. And as I said, so what's going to happen is I'm going to have the vertices, the edges. It's going to, of course, guess what the vertices are. And then it is going to also have a property for each edge that's going to be the weight, i.e. the number of passengers along that edge. And I'm further assigning, so remember that if you have a graph, probably I should show you this here. If G is a graph, then V of G gives you access in iGraph. I mean, V of G gives you access to the vertices of the graph, whereas E of G gives you access to the edges. And for example, if I wanted, because I've saved, as I said, this information about the volume here, if I go E of G vol, I'm going to get the volume along all of these arcs. Okay, it says edges, but it's an arc in this case because it's directed. Okay, so I'm putting the vertices where they need to be, which is in that vector lon and lat that I've created before. And then I'm going to plot this. I reduced a little bit the size of the arrows because otherwise it looks really ugly. Maybe I'll show you like this. Let me just cut this out. Just see, the arrows are very big, so you can make them a little smaller by doing something like this. And so here you see it, that's the graph. So Winnipeg is here, Brandon is here, DN, I don't remember what DN is. There's a lot of places that I don't know the code for. I remember them from time to time and then I forget. TH is Thompson, and this is YYQ is Churchill. That's about the only ones I remember off the top of my head. There must be, this is Red Sucker Lake. Anyway, so there's a few vertices. There's 24, if I remember what I was just seeing. 24 vertices, and this is the graph. With this is, remember, this is the rest of the world vertex, and so that represents all movements outside of Manitoba. I've put it here. It's not here, of course. It's just put it arbitrarily somewhere so that it doesn't show up too far away. I'll also make a subgraph without that ROW because we want to focus actually on travel within Manitoba, and it's not really important the travel elsewhere. But so if we do this, I'm using the command induced subgraph, which is simply a subgraph. This is the graph from which I'm starting, and then I'm selecting the vertices. So when you do a subgraph, you list the vertices that are going to be used in that subgraph. So what I want to do is I want to get rid of rest of the world. So I'm saying the name of the vertex is not ROW, and then I'm taking the vertices whose names are indexed by this. Okay. And so here I have the same thing as before, except that I've removed the rest of the world information. Now, one word of recommendation slash I don't know what is that when you're working with data, it's often good to spend some time thinking about how to show it. It is one thing to be able to perform an analysis of data, but it is also very, very important to be able to represent the data in a way that makes sense. So if you see this graph and you know context, probably you know what things are, but what I'll show you is how to make a map fit with this graph. Okay, and so it's quite simple. By the way, this command, I know some of you have found it before because I saw it in some of the assignments. Allows you to make bigger figures. So this is this just says that the plot that you're making is going to be from now on like this. This is a little I'm rerunning the code, so this was already set. When you run the code the first time, you will see that this graph and this graph are much smaller on display, and it is only when I turn this on that the graphs become larger. So what I'm going to do is I'm going to use the package raster, and with that package raster, I could use this function get data, and GADM is for Global Administrative Division Map. So this is saying get, and that's you need internet connection for this. Okay, this goes on the web and gets it. It gets the Global Administrative Division Map, and I'm asking to get Canada. And level 1. Level 1 is the top level. Level 0 is the top level map. So that would be just the map of the outline of the country. Level 1 is top level plus just below divisions, and just below divisions for us in Canada are provinces. Okay, so what I'm saying here is get the info for Canada with the provinces included. And so when you do that, okay, and then, okay, so before I show you some examples, then I want Manitoba. And so what I'm going to say is I get me those whose name 1 characteristic. So name 0 would be Canada, name 1 is Manitoba, name 2 would be the regions in Manitoba, and so on and so forth. So get me the data for those where name 1 is equal to Manitoba. Okay, and then plot Manitoba. Manitoba is a map. Once you've loaded raster, it knows how to plot a map. And then also plot the graph. Add that graph to the plot of Manitoba. So this add is true means when I say plot, again, don't start a new window, just plot in the previous window. Don't rescale things because by default, iGraph rescales the graph. I want it to have the same coordinates as the map, and then the arrow sizes and so on. Let me see. Yes. So you can see now I have my map of Manitoba, on which I have overlaid the graph with rest of the world and etc. Let me very quickly show you an example, a more complete example. So suppose that I have downloaded Canada, just to illustrate, so I can actually say plot Canada. If I do this, I'm going to get a map of Canada. It's going to take a little while because it's not okay. There it is. So there you have it. If you want to do some plots, it's easy to choose which, how to change the color in places and so on. This is just a brief intro, so I'm not going to spend some time explaining this, but it is very convenient to be able to show results if you're working on something that's spatial. Showing the results in a spatial way is really important. But important, I don't know, but very useful in any case. Okay, so we've got this map of Manitoba. Not very happy about the arrows still, but that's another problem. I'm particularly not happy about the vertices. So maybe just to show you that it's easy to do, let me do the same thing, but let me add the degree as an information. And often you will need a few times to plot to see what works well in terms of size. So here, the first time I plotted it like this, and it doesn't change much. I mean, so Winnipeg appears relatively big. This is the degree, so the number of, here I'm using the degree in both directions. We could also say degree out, for instance, the number of outlinks, mode out. Okay. But as I was saying, if you just do like this, then you end up with not a lot of information. So maybe if you're doing this, you could say out, it's probably going to be smaller. Okay, so you see, you can play with this until you have found something that looks to your liking, and then plot this. This is when I get rid. So here I'm back to using the regular non-oriented degree, so a total degree, and I have got rid of rest of the world. So here I'm only using Manitoba vertices. We can change the arcs, and one thing that we can do is, you see, so here I'm still using the degree like this, but I'm saying that the edge of width, so the width of the arcs, is a function of the volume. So when I do that, I have a very disappointing result, which I'll explain very easily. When you look at the volume out of Winnipeg or the volume out of rest of the world, maybe let's get rid of rest of the world and just stick to Winnipeg here, but it's going to Manitoba, but it's going to be the same idea. When I look at the volumes, I'm going to have some volumes that are going to be massive, and that makes a big arrow. Okay, so what you're seeing here is big arrows. So I'm going to, what I'm going to show you now, I'm going to spend a few minutes showing you pointless work. I'll warn you right away, you can skip ahead a few minutes probably if you don't like to see anything pointless, but I really want to illustrate the fact that a lot of what we do when we're doing research, or when you're working in a company and you've been asked to do something, you might lose some time. I always like to show things that are not perfect, because I think they are quite illustrative of the process through which you go through. And so here I was thinking, okay, if I look at the edge weight, so that's, remember, that's the number of passengers per duration of time, per some period of time, from one place to another. And I'm just going to look at the volumes. If you look at them, they go from 18 to 183,000. So what's going to happen is that if I use this as the size of arrows, it's going to be a problem, and I need to make those arrows smaller. So here, let me show you what happens when you take a smaller arrow. Okay, so most of the movement is between Winnipeg and the rest of the world. This is actually quite illustrative. It's a good information in a sense. It's showing you that most of the traffic is between Winnipeg and the rest of the world, and then there is rest of the world to Thompson, some flights to Churchill from outside of Manitoba, and most of the rest is from Winnipeg. Okay, and okay, this information is, but it doesn't look very nice. Actually, it's not too bad, but. And so the idea I had, so because look, I've multiplied the volume here by 10 to the minus 3. Here I'm going even a bit further, making the arrows a bit thinner between Winnipeg and the rest of the world, but some of them are becoming very, very thin. And so I was wondering at some point if there was one way to nicely recast the data in terms of volume so that we would have something that is more measured. And I'll give you the answer right away. I failed miserably. So here what I'm showing you, but I think it's an interesting exploration of what we have. So what I'm plotting here is the sorted volume along the different arcs. So there's an arc that has this volume, etc., and so on and so forth. And then there's an arc that has 160,000 or something, and an arc that has 180,000. So this is what is appearing there. And when you see that, you think, okay, so there's this sort of quick switch between situations. And one way we can model this in using a simple function is using what's called a sigmoid function, which those of you who will go into AI, for example, will see a lot, because sigmoids are used very often in neural networks. They have this nice property that they're small and then increase and then reach a plateau. And so there's this quick change of state as you go through a transition. So I'm using this function here, and what I'm going to do is I'm going to say, well, depending on the value of this constant c, I am going to get a curve that's going to change in size. And just to show you, I'm using vertices, which is, so I'm going to make that function as a function. So it depends on the value of x, but also c, the parameter c. I'm going to try a few values for c. And I'm just going to transform the data through this function to see what it looks like. And this is just making sure that I'm doing several plots, you see. So I'm going to try several values of c. These different plots that I'm going to do, I don't want to make a different legend every time, so I'm just being lazy and I'm using the vertices palette. So I'm changing the palette, and the palette starts with yellow. So when you see a yellow curve, such as here at the bottom, well, at the top of the figure, the yellow curve means that we are at it's the first value of c, and it goes all the way to purple. So the purple curve will be the largest value of c here, because they're coming sequentially like this. And I'm just plotting those different values. So in red, this is my original data. I've reduced, so remember I was going to 180,000. I am now reducing the values to be between 0 and 1, which is this thing here. If you're ever looking for a way to do that type of thing, this is one way to do it. So I've put the red values between 0 and 1, and I've also put the output of the sigmoid function to be between 0 and 1, which it will never be, because just in passing, a little bit of very simple analysis, if I put f of 0, and all my points here are positive, so but even if they were 0, then f of 0 would be 1 over 1 plus e to the minus 0, which is 1, so it would be 1/2. So that sigmoid function that I'm using here, there are several types, but that sigmoid function that I'm using here goes through 0 at the value 1/2. So if I did not do this transformation here, all the curves that I see, except for the red one, would start somewhere around here, around 1/2, okay? And they would go to 1. So these are the different values. I looked at this and I thought, okay, this is a bit better. That last curve to the bottom is a little better than the red one, because there's more distinguishment, more difference between the large values and the, between the small values, okay? So they're increasing, but it still remains quite clear that there's only a couple of values that are very large. So I thought, okay, let's use this. And well, it doesn't look so good. So I could probably spend more time and make that work. I am not going to do so. I'm just going to say, okay, let's stick to the original plan, and let's just do something like this. Okay. What am I doing here? I don't remember what I'm doing here. Oh yes, that's just whether we have rest of the world or not. And here, this is the graph for Manitoba. Okay, so this was sort of the preparation for what is coming up. I have about 30 minutes left. I think this should be good for doing this. If I don't make it by the end of this lecture, it will carry on to the next one, but I'll try to just limit it to this one. So now I'm going to go through several of the measures that we saw in the graph, in the course, and so I will start with eccentricities and things that are related. So here I have the course notes, and so I'll remind you what the eccentricity is. So we look at all the distances between vertices, and I'll just point out, so if you look at the help for distances, you'll see that they are, let me be a. Oops. So you see shortest directed or undirected path between vertices. I hope this is appearing in the video. I can't watch while I'm recording, so I'm just hoping. Where was this? Distances. You can choose the mode. Okay, so this is important, and this is what we'll see. Although here I'm only showing you the distances, the non-oriented distances. So non-directed, let me do distances like this, and let me do distances mode equals out. And if we took the time, we probably would find some differences in this table, but that's the equivalent of the table that we have there in the course notes, except that here it's 23 by 23 if we take the graph without rest of the world, or 24 times 24. We can look at eccentricities. So this is for each vertex the maximum of these values. And I should point out right away, before we go any further, this graph is strongly connected. Okay, so there's not going to be infinite distances in here. So that makes it a bit simpler. So let's look. I'm here forgetting about the rest of the world. Eccentricities, we can look at eccentricities with in direction, out direction. Then we can compute the radius and the diameter. The diameter, for some reason, I didn't remember this, but in iGraph, the diameter only has the non-directed case. Okay, so all directions. So eccentricities, you can see, so what's important here probably is to look at Winnipeg. So Winnipeg has an eccentricity of 2. So remember what that means. It means the longest, shortest distance out of Winnipeg, geodesic distance, is 2. So that means from Winnipeg, remember I said it's a connected, strongly connected and weakly connected, okay, graph. From Winnipeg, you can get anywhere else in the network in 2 steps or less. Okay, you can also take more, of course, but the shortest distance, the longest shortest distance out of Winnipeg is 2. Same way, Thompson is 2, so you can get anywhere from Thompson into 2 steps. That's what this means, okay? 2 flights. Whereas places like, I don't remember the names, Brandon, YBR is Brandon. So out of Brandon, the longest, shortest path, so the eccentricity is 3. That means there are some places that you can reach in Manitoba from Brandon that will take you no less than 3 flights. Okay. The radius is the minimum of the eccentricity, and these eccentricities, they're all regardless of whether you consider in, out, or all, they're all equal to 2. The diameter is 3. This means, again, that you can go from, this is the largest of the eccentricities. And I mean, so the function diameter does not consider orientation, but you could also very easily look at the maximum for each row and each column. So if you look at the maximum for each row in the distance matrix here, maximum by row is how long it takes, for example, from Brandon to go to, well, maybe I should show you this actually. Okay, let's do this. So I want to do this for each row. So that would be perhaps, let's see, mapply. Mapply is apply a function to a matrix. I need help for mapply. I don't remember what order things come in. Function and data. So if I apply the function would be max, and I want to apply it to the data being, for instance, this one. This is not what I was expecting. Okay, well, just by curiosity, we can probably do this. This is going to work in any case. Okay, so the diameter, of course, you can do it that way also. This one considers only in. This one, so let's do in and out. Okay, if the function won't do it, it's often easy to do it by yourself. So let's call it all in and out, like the previous one, except that in this case we have to use a function for, I mean, a computation to do it. Central points. Okay, so let me remove mapply. Maybe I'll check how to use it. Central points, center, periphery. So for convenience here, I'm going to write down what the eccentricity is. I'm going to do it in the out direction. Okay. The central points are the points which minimize, which have eccentricity that is minimum. The peripheral points, the points on the periphery, are the points that have eccentricity that is maximal. Okay, so this is what I'm plotting here. I'm representing here. So the central points are these airports, Winnipeg and Thompson being 2 of them. The periphery are all these airports. Brandon, for example, has an eccentricity of 3. And what I'm going to do, just to show you that it's easy to do this type of thing, I'm going to add that, okay, let's plot things in a way where I want to show the points that are, the vertices that are in the center as red, and those that are in the periphery to be blue. And so the property of a vertex that is used when you plot to determine the color of this vertex is color. Okay, so here what I'm saying is make all the vertices that are achieving, that have eccentricity that is minimum, therefore the vertices that are in the center, make them red, and those that are maximum eccentricity, make them blue. And when I do that, I get this. So here you see the vertices in red are minimum eccentricity, they're the center of the graph, and the vertices that are blue are vertices that are in the periphery of the graph. Okay, and that's an easy way to represent the information. So in all these red vertices, you can get to any other place in the graph in the minimum amount of time, well, flights, I should say, as required. Whereas if you're in one of the blue vertices, it's going to take you 3 flights or more to get to any of the other vertices in the graph. Okay. The girth, remind you that the girth function is undirected. Well, it assumes the graph is undirected. So if you look at the girth for G, so that includes the rest of the world, or for Manitoba, we both times get the same girth. And here it's indicating as part of a result which vertices form this cycle of length 3, which equals the girth. Okay, so here these are 3 here, and this is the girth here. The density of the graph, remember that this is, if we look at this graph and we're wondering, well, how much is missing until this graph is complete, so that every vertex connects to every other vertex, that's just edge density. And you can see that the edge density is about, let's say, if we forget about the rest of the world, it's about 16%. And I'll just make a remark about this. If I were to look at the more extended network, for example, the one in Canada, I would observe that the density diminishes. Okay, the more local the network, the higher the density. And if I recall, I'm not entirely sure, but if I looked at the same period for the density of the global air transportation network, so the entire system with about 4,000 airports, density would be about 2%, if I recall. I mean, it varies a little bit over time because there are some flights that are not taking place and so on, but that's essentially what we find. Okay, so Manitoba is much more connected, which makes sense. I mean, there's a lot of small communities here, and they do need access to the rest. Connectedness, well, no surprise, the graph is strongly and weakly connected. Okay, so the question might be, are there articulation points? And if there are articulation points, what are they? Well, the articulation points is, I'm just using the function articulation points. Just a reminder, this is another function that assumes non-directedness, non-orientation of your graph. So it's a little, there would be more articulation points if we considered directions, probably. I mean, although I should point out, in the case of the air transportation graph, it is very rare that there is no two-way connection. There used to be, actually, this one is interesting. This was an example I used to give years ago. This was a one-directional loop, or a cycle, sorry. If you wanted to fly to, I can't remember the name of this place, but you had to fly through Brandon and then here, or if you wanted to fly from Brandon, you had to go Brandon to this place to there. Now, apparently, it's both directional, so in a way, considering the graph as non-directed is not a problem. So what are the articulation points? Not surprisingly, if you cut out Winnipeg from here, you're breaking things. But also Thomson. Where is it? Thomson comes out as something that breaks the strong connectedness of the graph. And let's just take a look. So if I'm going to make a subgraph, but this time I'm going to remove Thomson. Okay, so I'm doing what I did before when I removed the rest of the world, but I'm removing Thomson. And so if I look at whether that graph is connected, it is not connected anymore, which is what we were expecting because we've hit an articulation point. And so what I'm going to do now is I'm going to look at the strong components and color them. Okay, so I'm going to say the components are this, and then I'm going to color the components, and then plot this and see what happens. And you can see it here. So in blue is the strong component that includes Winnipeg. So we've removed Thomson here. And so all the links that were going to Thomson or coming from Thomson, so all the arcs that were going or leaving Thomson, have now disappeared, and that gives us this result that we see here. So we've disconnected the graph, and we've actually made a couple of completely isolated places, and then two places that are just connected one to another. Here I've removed, by the way, I'll just point out, where did I do this? I have, yes, I have just taken the same size for all the vertices. Okay. Cliques. So let's look at cliques. Did I get this clique? Yes. So the largest clique, oh, it's not showing. Maybe let me list it. Yes, the largest clique has 5 vertices, and it includes Winnipeg, Thomson, and those 3 other places. And so what I'm doing this time is I'm showing these places in red and the other places in blue. And remember that the cliques, I could advance. Okay. So remember the idea, and it's we're in the directed case, so we're looking at definition 26 here. So the clique, although if I can't remember, yes, actually we're not looking at 26, we're looking at 24, because you see this warning message that shows up. Directionality of edges is ignored for directed graphs. So it is forgetting that the graph is directed, and it's just computing the cliques like this. And so the idea here is that all the vertices in this clique are adjacent. Okay, and of course you're not seeing it here, but so there's a subgraph here that I could extract, in which there's a link that we don't see. Yeah, we can see the top of the arrow there coming from Winnipeg into Thomson. And what that is saying is that if I look at that subgraph, there's a connection between all, it's a complete subgraph. Okay, it's K5 being the complete subgraph of on 5 vertices. Okay. So all the red vertices are connected to each other. So this is, from any of those places, you can get to the other places in one flight only. So this is a place where people can move easily between those locations. Centrality degree. So I've already done quite a lot of plots with the degree, so I don't think there's much to say about this. I yes, let me show you. So here I'm not using it. Let me use the out degree. What am I showing? Out degree, in degree, in degree. So this is for the general graph. Should probably show perhaps maybe. Let me do the graph of Manitoba, not because we don't really care about the graph the rest of the world in terms of what the degree distribution is. Is that good? Okay, so this is the frequency of vertices with a degree indicated on the x-axis. And so here, for instance, that is going to be the degree of Winnipeg. There is one place in the whole network that has a degree of 35. And if you, of course, I'm not looking at here, so black is the overall degree. So it's the first result that I'm getting here. This is, sorry, the third result. I'm not looking at the direction. So Winnipeg has degree 36. It doesn't have degree 36. It has degree 35 or 34, actually, because it's probably, let's see. Oh, yes, 34. You can see it here. And Thompson, I expect, yes, is the other one with a high degree, and all other places have a relatively low degree. So this is what this graph is showing you, and I've showed the different types of degree with different colors. And you can see, by the way, here blue and red are just overlapping. So the out and in degree of Winnipeg are equal, and Thompson are equal. There are some places which change a little bit, but that's the same. Finally, let's look at K-cores. I see the time is running out. I wanted to do this. You know what? I think I'll stop here. Yeah, I think I'll stop here. This way I will continue with just K-cores, closeness, and betweenness in the next lecture. Very quickly, we'll finish that and we'll go on perhaps another example. I have not yet decided. So this is it for the beginning of the Global Air Transportation Network for Manitoba. If you have any questions, let me know.